You're managing a hospital intake and testing process. Staff are arriving, checking in, and some need to go through testing before they can start their shift. But testing capacity is limited, so even if people are ready, they may have to wait until staff and resources are available. How do you balance arrivals with available staff? What happens when testing capacity fills up? And where do queues start to form? There's a model for that. Welcome to Model Monday, a series where we break down scenarios in different industries, organizations, and departments and explain how you can build a simulation of them in Process Playground. Let's model it. Process Playground has 3 different components to be aware of: items, blocks, and distributions. We're going to first create our item, then build out our blocks, then lay in our distributions and other parameters. First, we're going to create our item type, which in this case is called staff. This will represent all of the doctors, nurses, and researchers that are coming into work for the day, and this will be the item that flows through our model. Next, we're going to lay out our process with blocks, which is very similar to a value stream map or process map. We have different types of blocks that have different capabilities, and you'll see a lot of them today. The process starts with staff arriving at the hospital. We'll simulate this with the demand block. This block creates items to flow through our process, and we'll call it staff arrival. We're going to set the arrivals later on in the tutorial. Then our staff arrives in the parking lot, and if there's enough space, they will go into the lobby. So we'll introduce 2 queue blocks in sequence to represent these 2 holding areas. First, we'll make the parking lot queue, and then we're going to pull out a second queue to represent the lobby. This second queue will have limited space, and we'll show you how to set that up properly in just a second. Now that we have these 2 queues, we'll add our first activity block. Activity blocks represent time spent in the process. We'll call this block check-in terminals. This is where staff arrive at the hospital and complete the check-in process before either heading straight to the hospital or moving into the testing flow. The hospital has a policy for determining whether testing is required. So, after check-in terminals, we're going to branch into 2 possible paths. One path is for staff who do not need testing, and those staff will simply exit into the hospital. The other path is for staff who do require testing. We'll pull out this decision block, and we'll rename it Testing Policy. So first, we'll create the No Testing path. We'll pull out a queue block and rename it No Testing Required, and then we'll add that connection. And then we'll place an exit block here, exit to hospital. Next, we'll build our testing path. We'll add another queue block to represent staff waiting for testing related steps. And we'll connect that here to that decision block. We'll rename this queue Testing Required. After that, we'll add an activity block called Test Check-in. Then we'll add a second activity block called Test, which represents the actual testing process itself. Finally, we'll add an exit block to represent staff finishing testing and then entering the hospital. At this point, we have the overall flow for our hospital check-in model laid out. Now we can start filling in the parameters that make this process reflect reality. First, let's go back to the lobby queue. In reality, the lobby can only hold a limited number of people at a time. Process Playground allows us to create a constraint within a queue. In this lobby queue block, we'll set the max items parameter to 8. That means only 8 staff members can be in that lobby waiting area at any given time. The parking lot queue acts as an overflow buffer before that constrained lobby. So if the lobby is full, staff will continue waiting in the parking lot until space opens up. Next, we'll configure the check-in activity. This hospital has 8 terminals available for check-in, so we'll choose that in the activity block by setting the number of servers to 8. Then we'll define the processing time. For check-in, we're going to use a triangular distribution with a minimum of 20 seconds, a mode of 45 seconds, and a maximum of 75 seconds. Make sure you're using the drop-down here to select seconds instead of minutes. Now we can set up the decision block with the policy split after check-in. The hospital intends there to be a 1/3 chance someone will be selected for testing. So we'll set the probability of no testing to 0.66 and the probability of testing required to 0.34 so that they add up to 1. Process Playground will alert you if your probabilities do not add up correctly, and so you can make adjustments as you go. For the no testing path, once staff are routed there, they simply move out to the hospital through the exit block. Since there is no additional work on that branch, those staff should move through almost instantaneously. Now, let's configure the testing path. First, we have the test check-in activity. This step has a capacity of 3 people being served at a time, so we'll set the number of servers to 3. The processing time here is triangular with a minimum of 10 seconds, a mode of 20 seconds, and a maximum of 25 seconds. Again, make sure this is entered in seconds. Otherwise, you'll accidentally create a much larger bottleneck than intended. Then, we'll configure the test activity itself. This also has a capacity of 3 servers, so we'll set that to 3 as well. This is the part of the process that takes longer, so it'll often be the bottleneck in the testing flow. We'll use a triangular distribution again, with a minimum of 30 seconds, a mode of 45 seconds, and a maximum of 55 seconds. Double check again that this is in seconds. Now that the main processing blocks are set up, we can now introduce another major block to better make your model match reality: resource schedules. Resources in Process Playground can vary over time, which makes them especially useful when staffing changes throughout the day. So let's create a resource block, and we'll call it Check-in Staff. And we'll tie it to the check-in terminals using this dropdown. Then we can set the availability over time. From 0 to 60, we'll have 5 available. From 60 to 120, we'll have 6. From 120 to 180, we'll have 7. And from 180 to 240, we'll have 3. From 240 to the end, we'll just have 1 available. Even though the check-in activity has capacity for 8 terminals, the actual usable capacity is governed by how many staff resources are available during each range of time. This is a great example of how process capacity and resource schedules can work together and can be applied in other scenarios as well, such as checkout lanes and cashiers. Next, we'll create another resource block called Testing Staff. In this model, that testing staff resource will be tied to both the test check-in and test activities. This lets the same staff resources support both parts of the testing flow. So we've added both blocks to the connected activity blocks, and then we have to build a schedule. From 0 to 180, we'll have 3 testing staff available. From 180 to 240, we'll have 2. And then from 240 to 300, we'll have 1 available. This will actually create some time at the end where no one is available to work. This is another useful place to experiment with later if you want to see how changing staff levels affect queue growth and overall lead time. The next thing we want to do is put a limit on the number of people who are going to be in the testing process at a given time. So we'll add a core pull block. In lean terms, this behaves like a whip cap. More generally, it limits the number of items in a section of the process. We'll call this core pull block Wait for Test Capacity. We'll set the entry point for where we want the limit to start at the Testing Policy Decision block. Then we'll add both the Testing Required block and the No Testing Required block as the exit points. We'll set the capacity to 8. That means no more than 8 staff can be in this portion of the system at one time. This gives us a very practical way to model constrained flow and control how many people are allowed in the next part of the process. Now that the structure and constraints are in place, we'll finally go back and define the actual demand for staff arrivals. In this model, staff arrive at different rates over different ranges of time. So in the demand block, we'll create staff arrivals using an exponential distribution. For the first range of time, from 0 to 60, we'll use an exponential distribution with a mean of 10 seconds. Then, for the second range of time, from 61 to 120, we'll use an exponential distribution with a mean of 15 seconds. For the third range of time, from 121 to 180, we'll use an exponential distribution with a mean of 12 seconds. For the fourth range of time, from 181 to 240, we'll use an exponential distribution with a mean of 25 seconds. And for the final range of time, from 241 to 300, we'll use an exponential distribution with a mean of 120 seconds. This represents a very low probability that someone will show up late in the last portion of our simulation. Once that's in place, we're ready to run the model. We're going to run it for 330 minutes. As the simulation runs, we can watch queues begin to form, when the lobby fills up, and how the parking lot behaves as an upstream overflow area. You can also watch how staff move either directly into the hospital or through the testing branch, depending on the policy split. As we watch the model, we may notice that at some points there is very little queuing, while at other points there are surges. That's one of the main advantages of this type of model. It gives you a way to see when demand and available capacity are aligned and when they are not. It also gives you natural places to experiment later by changing resource schedules, queue capacities, or arrival rates. Once the run finishes, we can start looking at the outputs. First, let's look at the exit blocks. We're often concerned with total lead time, which tells us how long it takes for someone to get through the process before arriving at the exit. We can double-click the exit block, go to Results, and turn on Total Lead Time. Then we can use Apply to All Exit Blocks so we can compare both endpoints of the process. We can see that it took about 1.57 minutes on average to get checked in and into the hospital on the no testing path. For staff who went through testing, the average was about 2.8 minutes. These tables are a useful place for seeing how much extra time the testing process adds and to explore what happens if you change capacity or staffing levels. We can also use the total lead time graphs to look a little more closely at the lead times over the course of the simulation. Notice how they do cluster around this 1.5 minute mark, but some staff members took almost 7 minutes to get through the process. Now, let's take a look at resource utilization. This tells us how often our staff resources are actually being used. For the check-in staff resource, we see a utilization of about 63%. For the testing staff resource, we see about 49%. We can also open the utilization graphs to see how that changes over time. For example, there may be times earlier in the run when everyone is busy. Then there will be later periods where additional staff are present but not fully utilized. And finally, as staffing levels decrease, we still see that they're not fully utilized. We can also look at the testing staff resource and see how they were used over the course of the simulation. Notice the little step stair down as we reduce the number of staff later in the day. Resource graphs are a great place to understand where staffing is aligned with the arrival pattern you're modeling. Then we can look at the queues. Since the lobby queue is constrained, it's a particularly interesting one to inspect. Let's take a look at the queue length over time. We can see right away that the lobby was full, but as soon as the demand went down and we had more resources on staff, we were able to catch up and maintain over time, just with that one little spike. We can open the queue results and look at the metrics like count, average length, and max, and then apply those to all queue blocks. The parking lot is unconstrained, and so we can see the buildup right at the beginning, but it goes down to manageable fairly quickly. Finally, we can look at the testing required queue length and see how it was affected by the core pull block and the resource staffing as well. We can now look at the activity blocks. Here we can inspect metrics like number of servers utilized, runtime, and idle time, and then apply those settings to all activity blocks. For the check-in servers activity, it becomes especially interesting because even though we created capacity for 8 terminals, we never necessarily use all 8 at once. The actual utilization depends on the available staff resources. So this gives us another nice example of the difference between capacity that is available and resource-constrained capacity. We can do the same for test check-in and test. The test check-in step hardly ever reaches all 3 servers, while the test activity more often approaches full use, though not always. Again, these are useful places to experiment. You can compare activity behavior against queue growth and resource utilization and see how different features of the model interact. So in a nutshell, that's the hospital testing model, but the real value is in what you can experiment with. By modeling how staff move through check-in and testing, and by limiting capacity based on available resources, you can see how queues build up and where bottlenecks form when demand and staffing don't line up. And it's not just hospital testing. The same pattern shows up in airport screening, employee onboarding processes, manufacturing quality checks, or any system where people must wait for capacity before moving forward. From here, you can start to ask real design questions. How many check-in or testing staff do I need? How should I schedule those resources throughout the day? What happens when arrivals increase but staffing stays the same? Or when one step becomes constrained? Those are the kinds of trade-offs this model is built to explore. That's the model. Now go experiment. Happy modeling!